So for our last video here on chapter 17, we're going to be looking at some more aromatic reactions. So we're starting off here looking at the nucleophilic aromatic substitution reaction. So the NAS reaction versus the ones we're looking at so far, those electrophilic aromatic substitutions. So this is a little different, right? Where now the benzene is, right, our benzene is the nucleophile now, or sorry, it is the electrophile now, right? We're adding something to it, right? We're adding a nucleophile to it, and there's a few reasons how we can get that to happen, right? So we need to have, like we're seeing here in our reaction where we're making an ether, we need to have an electron withdrawing group, and then we need to have a good leaving group, okay, which this chlorine is. And we need to have a strong nucleophile, which we're going to be generating, especially when we add in our tert butoxide here, right, which is a really strong base, which will deprotonate, right, our phenol here to get to our proper nucleophile. So what does this reaction look like? Or the mechanism, rather. So what we're seeing is, right, we have our chlorine, NO2, and I'm going to skip the step where we deprotonate the oxygen. But right, that's what that strong base is doing here, it's deprotonating it. And so we're going to have our deprotonated phenol come in and attack the site here where the chlorine is, right? And the chlorine is also, right, being electrophilic, right? But it's also a good leaving group, so that's why we're having our phenol attack here. And we're going to generate, instead of a carbocation intermediate, we get this carbanion intermediate instead. So we have this as our intermediate now. And it's important to recognize, right, we're making, I'm going to abbreviate the benzene ring as pH, right, for phenyl. You're free to do that too. The intermediate here, right, is a tetrahedral intermediate, which we learned about in those earlier chapter videos, right? This is a stepwise mechanism, right? So we can't do, right, we can't do SN2 reactions on sp2 carbons. So that's why we have to do this pathway, right? We can't just have our nucleophile come in and kick off the chlorine in one single step, right? So on SN2 we have to do this concerted, so we have to do this stepwise. So we have to go through this tetrahedral intermediate, okay? And so after this, right, we reform the aromaticity, which kicks off our leaving group, right? Chlorine is a much better leaving group than the O-, which gets us to our aryl ether up here as our product, okay? So important thing to note here for these NAS reactions, they only happen again when we have a electron withdrawing group, right, and when we have a really good leaving group like we have here. Okay, this is kind of similar to that Sandmeyer reaction, right, where we had, right, N2 plus here as our leaving group, right, because when we do that reaction, right, we add something to that, we end up losing N2 as our leaving group. So these, again, are the conditions we need, right, strong nucleophile, good leaving group, and electron withdrawing group under benzene, because otherwise we don't really get this happening, okay? Or rather, it's harder to, and we'll see an example of that. So we'll do these two problems here in class, where we're going to look at a couple of examples of this nucleophilic addition here, okay? But one other mechanism I wanted to show you, which is something else that can potentially happen, is through a different mechanism, so this elimination addition mechanism. So I'm going to zoom in here a little bit. So notice on our molecule now, we don't have a electron withdrawing group, right, we just have a chlorine, right? So it's not as electron poor, but we have this really good nucleophile, right? N minus, right? Anything with N minus is a really, really, really good nucleophile. So it's really reactive. Okay, and that's kind of the crux here of this mechanism that we're going to see. And so what's happening here is instead of attacking that carbon-chlorine site, it's actually going to eliminate, right, it's the first part of this step here, we're going to eliminate hydrogen. Right, and that actually gets rid of the chlorine. So there's a good nucleophile. I should also be saying, right, it's also a really good base, which is what it's doing here. It's acting as a base. So we get this unique intermediate here called benzene, right, which only exists very briefly, but as you can imagine, is extremely reactive due to steric strain, right? And also, right, it's really ring strained, so it wants to react pretty immediately. So we actually end up happen is we have another equivalent of that N minus, which now acts as our nucleophile to come in here and generate our anion. Which will get protonated by something. This remaining equivalent of our material, most likely, will come through and will protonate our carbanion intermediate here to get to our product. So this is really niche, and I'm not going to expect you to know this mechanism to draw on the exam, but this is an example of something else that can happen. Okay, this is another potential way we can get to our products here. And sometimes we can only figure that out, right? I'm kind of showing you multiple mechanisms, because sometimes this is just the case, right? Sometimes there's not really one mechanism that looks, quote unquote, better than another, and sometimes it's up to chemists to experimentally confirm one pathway versus another, right? So for example, if this benzene here was confirmed experimentally during the course of the reaction, they can say, okay, this is the mechanism taking place. Otherwise, it would be our traditional, right, nucleophilic aromatic substitution versus this elimination addition. Okay. So to finish off here, let's look at a couple more reactions. So we're going to look at these organometallic reactions, and these are really not niche, but they are these extremely sorry, I have to go back here. These organometallic reactions are these really versatile, widely used reactions because they work just so well, okay? And when we say organometallic, what we're referring to is the fact that we're having, right, organic compounds and we have a metal we're using. So these are organometallic reactions. And this is kind of a complicated system, and we can't really look at the mechanism, right? Mechanisms are complicated, and there is entire courses for that, like inorganic chemistry and organometallic chemistry. So because they're complicated, we don't need to know them. But I'll give you the rundown of what's happening for each of these. So we're going to look at two here. So we're going to be looking at the Heck reaction and the Suzuki reaction. And for the most part, all of these are making new carbon-carbon bonds, right? Like the Grignard reaction, which is sort of organometallic on its own, can make carbon-carbon bonds. The same thing is happening here, okay? And so what we're going to be seeing is for each of these, and this one in particular, right, we're using palladium. This is our catalyst, right, which typically means we're using less than 5% of it based on everything else. So the catalyst regenerates in the reaction, right? So it helps facilitate the reaction, it reforms, and it continues to facilitate the reaction. We have a base, which just helps to promote the reaction, and then we have something called a ligand, which I won't go into great detail about, but a ligand is essentially this thing that will coordinate with the metal and help this sort of process, right? Helps this sort of metal shuffling going on that gets our two components here to connect to each other. And so for our components here, right, we kind of have a really short list, or we have a shorthand list of things. So aryl or vinyl groups for R, and by that I mean aryl refers to, it's essentially phenyl, but we can have other things attached to it. So aryl is this, so it's any sort of phenyl group, and we have other things attached to it. So we can also abbreviate that as R. But aryl is just another way to say phenyl, essentially. And then vinyl is sort of new. It essentially refers to a double bond like this. Okay, so it's like an example of what's happening here. And the reactions are pretty simple, right? I kind of did do a lot of explaining here, but the way we connect things, again, we don't need to know the mechanism. The way we connect things are really simple. So we have these two species here, right? It's always going to be that we have a halogen, right? So we should be looking at that particular carbon for the connection. And then for our vinyl species, we should be looking at this species here. And what it does is, right, we're connecting the alkyl species with the double bond. Okay? And so the product here that we're generating is this. Essentially just removing that bromine, making a new bond to that alkene there, just like this. Again with right, those palladium conditions, right? So we have palladium acetate, the ligand, and then our base. And we're making this new carbon-carbon bond here. Okay? And that's generally it, right? And this is good because we can't use, right, there's no other way we can really connect double bonds to benzene rings. So this Heck reaction is going to be pretty important if we want to attach a double bond in any particular way, okay? So the next reaction we have to look at is the Suzuki reaction. And it performs in a very similar way, but we can really attach a lot more things. Or rather, it's more versatile. And so what we can do here is we are essentially, you know, it's the same as the Heck in a lot of ways, or, you know, similar rather. Similar to Heck, right? Another organometallic reaction. Where we have different catalysts we can use. The one I'll probably be referring to the most is this top one here, this palladium tetrakis, NaOH is what it's called. And a lot of these palladium, like, we have a lot of different palladium conditions we can use. Sometimes some are used over others because of the oxidation state, right? Palladium can have different oxidation states, and that kind of changes the reaction conditions. But for the most part, right, we're just going to be looking at this one here. But you can use any of these conditions that I've listed. So what essentially happens is, again, we're making another carbon-carbon bond. And the end result, I drew that wrong, sorry, is that we're connecting the two R groups here, right? There's not going to be a double bond in the middle. So we're just going to be connecting this R group with this R group, okay, to make this new bond here. Using, again, similar to before, we have this, we're going to have a halide species, and then we have something called a borate ester or acid. Acid refers to when we have, as above, this double OH species, and ester refers to when we have this B methoxy type species, right? And it's kind of confusing because it's not, it doesn't look like an ester, right? It looks like an ether. But that's what it's called. Okay, so this is called a borate ester. And to make borate esters, it's similar to what we've seen with Grignard reactions. So taking a species like this, an alkyl halide of some sort, right, just like Grignard reactions, and then substituting in lithium. You could substitute in magnesium as well. right, to get to a, right, nucleophilic or more nucleophilic benzene, and then reacting it with this species, and we essentially get a substitution reaction occurring where we generate our borate ester. Right, and this is the species that's going to react with something else that we want to get to our new carbon-carbon bond. For example, again, we have a different alkyl halide here, plus our borate ester, right, which is the same as what we drew here. I'm just shorthanding it like this, right? And with those palladium conditions, this palladium tetrachus, or any of the ones I listed, are totally fine. Base here, we end up generating a new carbon-carbon bond, like this, with a methyl group in the back here. Whoops. So the methyl group hasn't changed, right? I'm just kind of showing the differences in how they're connected. But again, we're generating, right, this new carbon-carbon bond from, right, these two species here. And we don't have to use, even though I'm writing aryl or vinyl, we could also actually do these with alkyl species as well. So we could even do something like this, where we have, right, if we change this one aryl group here, we could do something like this instead with our borate ester. Same palladium conditions, I won't rewrite them, to get to our product. So this is also totally fine to do, okay? But in short, right, these are kind of these niche reactions here that are always going to be, or I'm going to try to make them simple, right? Just showing that we can make these new, right, carbon-carbon bonds between two species, okay? So we'll definitely talk more about this in class as well.